I want to start with a story today. This is a story about a friend of mine named John who used to work at a big aviation contractor, software engineer. And they walked into a meeting one day, and the client came to them and said, here's $1 million, and here's a deadline that's a year out, and here's a little chip. And your job is to make sure that chip doesn't kill people. And the chip's already done. All you need to do is test it. What the chip was it was a sensor that goes inside of landing gear, and it detects extreme temperatures and extreme pressures and atmospheric conditions that might be a red flag that if you were to open and engage the landing gear would stick, and then the plane would crash, and it wouldn't know that the landing gear was stuck, and then it would, tumble around and kill everyone. So clearly, lives are on the line. It's a really important thing that the tests prove that this thing works as we expect. And normally, our response, we approach testing as make sure it works, prove that it works. But in this case, we couldn't do a realistic test. What's a maximally realistic test for this situation? It's, of course, put the chip in a bunch of planes, load those planes up with people so that it's the right weight, wait for inclement weather, take off, and then keep crashing plane after plane of people until the chip works. And then, you know that it'll be safe. So if our tests, when we use the word test, the BDD movement, Dan North and everyone talked a lot about how the importance of words that we use to prompt ourselves matters. When we use the word test, we think of examination. We think of verify that it works the way that we think it should work. If our test exists to prove that our code works, then the word fake or anything less than real feels like it's a cheat, feels like it's something less, like we're taking away from the value of the test. And so we like to think that all of our tests are real. Web applications are certainly much more simple than testing landing gear on an airplane. They're usually not life critical. But we're all cheaters. We cheat in all kinds of ways, and the difference is that we just all agreed these are okay ways to cheat. And we don't talk about it as if we're faking stuff. Some examples, like Selenium, we use a fake user, and we tell that user, what to click on with the keyboard and mouse and how to do that, and it follows our instructions over and over again, every time, with no variation, no randomness. And that doesn't sound like a human at all, right? This totally unrealistic way to actually drive a web application. That's not real. Test data. Most runners will clean the database on every run. And if you've got a long-lived app and you've got years of data migrations and your production data, your users have had to suffer all your little pedantic column changes for years, your tests, no problem. Your tests don't see that because they get a clean run every time. And your tests aren't going to catch that. That's not realistic. The runtime is usually started over again for every individual test or test run. So if you've got some sort of subtle memory leak that's occurring, and your application gets bogged down over time or starts failing, in complex, long-running situations, your tests don't see that. Your tests are fine. It's cheating. Another one, tests run against usually just a single process or even a single-threaded, runner or server, whereas in production, if we scale, we've got all these servers running, we've got load balancers, we've got all sorts of potential race conditions lying in our code, and our tests can't do anything to find them for us. So we're all cheaters. And we're cheaters because reality is expensive, right? It would be really expensive to hire a whole bunch of people in focus groups and have them just live in a lab all day, every day, and make sure that our code works on every commit. So if reality is expensive, why don't we budget it? Why don't we be more, intentional about thinking about this sort of scale of how real to how fake is it? We can't always have pure reality, so let's try to figure out, how much we need. So instead of asking, is this test too fake? I don't know how good the slide is, but that's a fake plastic cow with little rubber teats, and they're milking it. It's possibly a too fake cow. Instead, we should be asking, how much reality does this test need? We're turning the whole question on its head. How much reality is this test worth? Is it worth 8 bits of Mario, or 16, or 64, or that guy? A real plumber? Every test has different needs. These are things that I've overheard at conferences. Spoiler alert, most of them are Ruby conferences that I hear things like this. Platitudes, like mocks are good, and then some other dude who's like, no, mocks are bad. Or only mock what you own, which is a very cryptic phrase. that if you read the book Goose makes sense to you, but is otherwise confusing. And so somebody will interject and say, no, you only mock external systems to speed up the tests. Totally divergent opinion. Or, mock everything, mock all the things. Some people mock everything all the time to the point that you're really uncomfortable. And then on the other hand, you'll have some voice of reason enter the conversation and say, no, you should avoid over-mocking, but with no qualification as to what over-mocking means. So we have a lot of platitudes that we pass around about faking stuff in tests, and I want to just step back and start to have a more formal discussion, because what I'd really love is some nuance and some rigor to how we approach test doubles and just general thoughtfulness. It's really up to us what we want to get out of our tests, and it's up to us to decide how much reality we need for each type of test and what the consequences of that are. It's a maturity level thing with respect to our testing. And I think it flows really well with the first two talks today, because a lot of that is about long-term sustainability, object-oriented design, and knowing what we're doing while we do it and why we're doing what we're doing. So first I want to talk about types of tests, just so we can have a common vernacular today. These are terms I tend to use to discriminate different kind of like gradations of fakeness. First, let's start with an end-to-end test. Now, an end-to-end test, the real application is a black box. We've got this dog app. And we have a separate application that runs in its own process that is strictly there to exercise the dog app, make sure that it works. It probably uses the dog app the same way a user of the dog app would, whether that's a web interface or a command line. So I call those end-to-end tests, full stack. Integration tests, still a big black box in a sense, but we have visibility to the object model. We're probably running in the same process as the objects that we're exercising. And here we have a dog feeder class. So just to explain this really contrived example, a dog feeder, let's say, is a class responsible for feeding dogs, and it needs access to a bone repo so that it can go get a new bone, and a dog repo so that it can save the dog after it's given it a bone. And both of those repos talk to a database. Really important stuff. I can't do landing gear. I'm not smart enough for that. So the dog feeder test talks to a dog feeder. The dog feeder then still has realistic relationships with all of the units around it, and it's still talking to a real database. So an integration test. A unit test, Michael Feather's 4 rules of unit tests. I won't rattle them off, but they include no network access, no file system access. A unit test shouldn't be making network connections, and so a unit test fakes out the database layer, and then this black box shrinks. There's still a significance to the black box. The black box here means these are all the objects that we own as part of our application. And so when our dog feeder test exercises a dog feeder, it has already set up the fake database, but it's still talking to a real bone repo and a real dog repo, and those things all of our objects are real here. So that I call a unit test. Now an isolation test, and the number of arrows I realize is intimidating. Here the test, all these green things are things that are owned and taken care of by the test. So we have a dog feeder test. It is creating some kind of fake dog repo, some fake bone repo, injecting those into the dog feeder so that we have complete control over that interaction. And the test coordinates all of that. And so when we exercise the dog feeder, our test becomes a complete specification of everything that the dog feeder object does, and including how it relates to its collaborators. If you're doing test-driven development, that means that our test is helping us discover what collaborators the given object needs. So that's an isolation test. Now when you want to talk about mocks, a mock is really, it's the popular term for any fake thing that we use in place of a real thing when we're writing a test. A test double is just a more precise term. We use the word test double because mock happens to be a very specific subtype of a fake thing. And because that name was taken, Gerard Mazzaros, who wrote the X-Unit Patterns book, I think he was the one who came up with the phrase test double. And the reason he did was he wanted you to imagine the word stunt double, because this is a fake object that stands in place for a real actor in your test. So if you ever wonder why test double is named that, that's why. So a test double, just to kind of draw hierarchically different types of test doubles, it's our catch-all term. A fake, typically we roll our own fake objects, but they're usually just convenient test scope implementations. So for instance, imagine we have a network data source and the tests are slow, or it's hard to get a repeated behavior out of the network data source. So we just create a fake file data source, and we might instantiate it. We just make sure it quacks the same way as a normal network data source so that we can hand it to our dog repo, and then the dog can just kind of be on its merry way, not knowing what type of data source it's talking to, just that they both adhere to the same contract. A stub is a test double that is pre-configured to respond to messages. So you inject it into the thing that you're testing, and if you say, for instance, I'll show a quick example. We've got a database class, and then I'm using a test library I wrote called Gimme to create a test double for us. And we say, give the database, whenever it receives the message find with the argument 1, return me an order. So imagine some fake order object. Then over in our production source, whenever we say database.find and we pass it the parameter that we're expecting, we'll get the order back. And we're able to facilitate that downstream behavior in the subject code that we're trying to exercise for our test. You could roll your own stubs, lots of people do, or you could use a library, and there's no shortage of them to do that. A mock is actually a special subtype of a stub. So a mock is a stub that is pre-configured not only to provide responses to messages, but to expect certain invocations take place. So here's an example from Mocha. I'm faking the same database here, but with the mock method. And then you can see it uses symbols to indicate what it's talking to. So the database expects the method savebang with the parameter dog. And then over in my production code, if it calls database.savebang with dog, back in my test I can run database.verify, and no error will be raised in the event that the invocation occurred as it was expected. And if you use Mocha and you don't run database.verify, it's because it's usually set up in our environments to auto-verify as part of test cleanup. A spy is like a mock. It's also a special subtype of a stub, and it's meant for the same purpose, to verify that behavior takes place. But instead of preemptively expecting invocations take place and blowing up if they don't happen, it just records everything that you give it. Everything that happens, and then you can interrogate that later, and you can assert against the spy, just like you would assert, like arrange, act, assert, given, when, then, any other normal assertion. So it fits in a lot better with your existing tests that just test return values. So here I'm using gimme again, asking for a database, and then over in my production code I'm saying, hey, database.savebang dog, just like I did before. And then I've just got the final step is to add a test to say, hey, verify that database got the message savebang with the dog. And that's a spy. Fantastic. So those are all the types of test doubles. But that doesn't give you a lot to take home right now, because it doesn't say anything about how you should use them. Well, you should use this one here and use this one here. And I would plead with you to hold your horses, because I'm really afraid of putting the cart before the horse. The last thing I want to do is add to the list of platitudes about the right way to use mocks. We've got plenty of them. What I'd much rather do is ask the question, why should we use them? And start to just run through a couple of quick exercises so that we can kind of analyze, what are our motivations for testing? Why do we test? How much reality is that test worth to us? Does it really need to be useful? And then we can have a conversation about different test strategies and where mocks might make sense for you and where they might not. So here are some different motivations for tests. Acceptance testing is commonly used to describe an end-to-end test that proves that the application works like you promised, either to a product owner or to a customer or to you 6 months from now, that it's still working. I'd say it's about a real plumber's worth of reality to make sure that your acceptance tests mirror reality, because you want to make sure that it's really, really working. It's the one type of test where you don't want to add any fakeness that you can't afford. Specification, we talk about tests versus specs. When I say specification, I'm talking about it's a test that has some regression value. It is exercising the code, but maybe its primary value is to give the next guy a chance to make safe changes to this code. And a big part of that isn't just green specs. It's being really readable and clear and concise. So it needs some reality. It's not totally contrived, but it's more important that what you're looking at be really readable and clear. And so I'd give that a 16-bit Mario worth of reality on the spectrum. Regression, meanwhile, we talk about regression. A bug occurs, and then you want to go write a test to reproduce the bug, fix the bug, and then go green and make sure that the bug doesn't come back. Here, reality is relatively important insofar as we realistically reproduce the bug. But typically, we all have experience finding bugs. Typically, it's a very tiny little narrow thing. So as long as it's realistic to that extent, that's cool. But it probably doesn't need to know about the whole outer application. So I give a 64-bit Mario to that. Design, another motivation for testing. If you do TDD, a lot of people talk about test-driven development as test-driven design. If the purpose for you writing this test is to figure out what you need, to discover what the API should look like, what the collaborators are, you're thinking about the code, you're thinking about the architecture. You're not necessarily thinking about how that code fits into the bigger application or serves the purposes of the application necessarily. And so here, reality, its value is negligible. The regression value of most design isolated tests is relatively low anyway, so trying to add a little bit of reality to feel better is just that. Characterize, another motivation is we've got legacy code and we don't know what it does, but we know we have to change it, which is dangerous. So we write characterization tests to make a black box out of it, test the inputs and outputs, and then make our change and make sure that it's still behaving exactly the same way that it was before. And here, it's just like with regression. You got to find a seam and isolate this area very realistically, but the broader application might not care. So yes, some realism is important, but we don't need to hire the full-time plumber. And so this is just, these are some of my opinions. I mean, this is stuff that I run into. I'm sure you could classify the tests that you write similarly, and maybe you have different motivations. But my point is, we should always be asking ourselves, what value do I hope to get out of this test? What's this test worth to me? If I'm spending 10 hours on a test, I really hope that I'm getting a lot out of that test, right? So I want to talk about strategies for tests, strategies and how testables fit into those different strategies. It's a map. So one strategy on the far end of the spectrum of trying to maximize realism, some teams are oriented towards writing tests that just prove it works. It's all they really look at testing as. I think it's a popular view, I think, in this community too, is that the purpose of tests is to make sure it works and then we move on. So the hallmark is it minimizes fakeness, and we tend to only write end-to-end tests and integration tests. We don't fake out databases. We certainly don't mock out code that we own. And the value cost analysis here is that the value is that you have a high confidence that a green build is a working build, which is really important. I've had tons of green builds work in the past on teams that ended up really not actually working when you tried to use them. So that's the key benefit. Another is that if you write fewer tests, you spend less effort on tests. And if you're getting the value that you need out of it, you can just stop there. But a cost is that the tests themselves, because they don't see typically your object model or not very much of it, they can't provide you many design clues in terms of whether or not you're designing that code well and to be changeable and to grow well with you. And so you might find yourself painting yourself into a corner and wanting to do a big epic rewrite later. Slow feedback. So if your goal is to prove that it works and to know whether your changes are still working, it's still important to have fast feedback. You want to know that right away. You don't want to wait 3 hours and then find out that you broke something if the important thing is proving it works. But the problem is end-to-end tests, integration tests tend to be slow, and if you try to get high coverage with end-to-end tests and integration tests, you're going to have a nice big slow build, and it's actually going to kind of kneecap the whole goal of make sure our tests are realistic so we always know that the code's working. Another strategy I'd call mocking boundaries. And this is a strategy where we're willing to fake remote systems and network access, maybe some file access, but especially third parties like Twitter, Facebook, and integration points like that. But don't actually use testables to mock out stuff that is code that you already own, that's available and predictable. Instead, we write unit tests and end-to-end tests. So we write, we fake out the external stuff, kind of like we saw in the picture before, and we write a lot of unit tests against that. So a benefit to that approach is that each of our objects, if they each have their own unit test and they're also used by all their collaborators, they get tons of redundant coverage. They're used 8 ways to Tuesday. They're used by many different tests under many different contexts, and they have a higher regression value. You're very likely to be surprised, oh wow, that broke that test over there, and then you realize that somebody's assumption was wrong or the code didn't work. So they have a higher regression value overall. Plus they're obviously faster than integration tests. And they're also, they're very practical, but without requiring a deep expertise in some of the advanced techniques that you need to know to be really, just competent using testables and isolation testing. So a cost, though, is that redundancy it can be nice for regression, but it can be a huge burden for change. One change occurs, and then a 30 test break. And if it's because you've got one little object in the middle of your application and it adds 1 + 1 and it gets 3, and somehow everyone else started depending on that, and you have these complex reports and this complex math, you go in later and you fix that to 1 + 1 = 2, and then all of a sudden you've got 482 instead of 567 on this other test over here, and you've got to really kind of get back to the mental state of where you originally were, because the test doesn't codify those assumptions. It only has that real collaborator set up. So there's a real cost to that. It's exacerbated by the fact that unit tests by themselves don't tell you the app works. So you still need end-to-end tests that go through the whole system. And because you have end-to-end tests, they're going to do the same thing. They're going to provide yet another instance of coverage over all the same objects again. And then one change means lots of fixes to my other unit tests, and probably lots of fixes to my end-to-end tests, my cucumber tests. So if you fall into this cadence where you make a change to the application, and maybe you don't test drive it because you have slow feedback already, and then you are finding that a day of changes results in 2 days of fixing all of the tests and the other things that it affected, maybe this is the path you've gone down, and maybe it isn't working for you very well. Even with unit tests, even if you're practicing TDD with unit tests, you get good feedback about the API like I mentioned earlier, but you don't necessarily get as good a feedback about abstractions, about how the code collaborates with other code and its dependencies. So here's somebody thinking really hard, case by case. Let's just roll with the punches. And here we cater our testing approach to the needs of each individual test. So really it's a tactical approach as opposed to a strategical, more, you could say more disciplined, but really it's just at what layer are we applying that discipline. Value of case by case is, it's developer freedom. A developer is the one closest to the work. They can choose the best tool and the best approach for each individual job. And in general, we should trust people to do the right thing who is closest to the work at the time. Because if we decide something big up front, about a strategy, there's going to be times where that doesn't fit. And then what do we do? And in general, I think it's always safe to start here. Start with maximizing people's freedom, and then when things, when the wheels fall off, get together as a group and try to figure out how to change course. So that's a huge value in my opinion. And you'll fit right in on most Rails teams is another bonus. I think most of the Rails teams I've seen tend to act this way without a whole lot of metacognition about test strategy and what are we really here for and why are we testing. And they kind of naturally just fall into this case-by-case mode where every developer and every pair kind of makes the decisions about what they want out of this test. And unfortunately, a con is that it's not often obvious when you come back to it what the original author's intent was, because it's different for everybody. Con here is that test doubles often get abused. I would guess on most Ruby projects I've seen, Rails projects, excuse me, a majority of the times I see people use mocks or other test doubles, it's as part of a Rails model or a Rails controller test. Now, obviously, Rails model tests, Rails controller tests almost always need to actually talk to a real database, so they're integration tests by default. And if you're mocking and stubbing stuff in them, then you're taking away from the value of the integration test to tell you that it's really working. So you end up with this weird, awkward mix and match of fake and real, especially in these in a lot of traditional Rails tests. Then the value becomes really murky. Is this test here to help me drive the design, or is the test here to prove that it works? Well, it's fake, so it won't, and it's integrated with the database, so I don't have the control to really help drive the design here, so I'm not getting that feedback. And what I suspect is happening is that somebody's writing an integration test, somebody's writing a Rails test, the code is trying it's busting at the seams, and this test is too hard to write. And that pain in TDD, we should respond to that pain by trying to change our design. Fix our design so that the test isn't so painful. But the easier thing to do is to grab a tool out of the toolbox and plug it into just, so many test tools exist in Ruby just as sort of a salve. Let's make the pain go away, let's use a mock here, even though it doesn't really make any sort of cohesive sense, and get this test working. Another example of a similar pattern that I see a lot is the reliance on heavyweight shared fixtures and factories in Ruby projects. I think those just tend to become dumping grounds. And then the last thing that I think on a personal level, this is my least favorite bit about this kind of willy-nilly case-by-case approach, is the conversation a pair has where one pair likes mocking and one pair doesn't like mocking, and then they stop for every single collaborator and have a really low-value decision of, hey, do you want to mock that one? No, we shouldn't. And you end up arguing over this stuff that really, at the end of the day, doesn't matter very much. The last approach I want to talk about is growing object-oriented software. So often we call it Goose. So when I say Goose, I mean this book by Steve Freeman and Nat Price. What it advocates is we use isolation tests to drive the design of the objects that we write, all of our code, and then we still have end-to-end tests to prove that it works. So to any extent that somebody could poo-poo us for the fact we're writing these isolation tests that don't have very much regression value, we can at least come back with the argument that, hey, we've got these high-level end-to-end smoke tests to make sure that everything's plugged together right, and the basic uses of the system, do in fact work. And I found this balance to work really well for me personally. It means I only have a handful of end-to-end tests, so my prove it works build is relatively fast, and I find out when I break something relatively quickly. And my isolation tests are ridiculously fast. So I was fortunate enough to be here last year. I want to thank the organizers and all of you for welcoming me here again this year. Last year we talked about Jasmine, right? We talked about testing JavaScript with Jasmine, and Jasmine kind of forces you into isolation testing by default. Because it's really hard to do integration testing there. And so I've done several projects now with 4,000 specs, and each of them runs in under 3 or 4 seconds, the entire suite. That's a huge asset. It's a huge benefit, and that, like we were doing with Ben's refactor example today, having fast feedback from his specs is why he was so productive. If his specs took 30 seconds for Rails to start up, and then he saw the feedback, he'd lose interest almost immediately, or he'd lose his train of thought in what he was trying to do, or he'd make too many changes and get in a big quagmire, and then just throw it all away, get reset, and then commit and go home. I don't know you, Ben, but sweet. Me too, I'm that way. So the Goose Way, the values here is a primary value if you practice TDD is it does give you that rich feedback about abstraction points. If you've got something that's hard to mock or hard to test, or if you end up with a whole bunch of 15 lines of test double setup code, which I know everyone hates, everyone should hate, when you have that, that means that your abstractions might not make sense, and the collaborations between the subject that you're testing and its collaborators probably need to be rethought out. Maybe you need some new intermediary collaborator to take care of some responsibility. I love getting that feedback in a test because it's a nice, safe, simple, incremental way to get that. They're consistent, so when you don't have to set up real objects, because every object likes being set up in a particular way in real life. When you don't have to set up real objects and you're setting up fake objects, especially if you're using a library to do it for you, that setup starts looking really, really consistent once you get used to this. I love that. They're fast, like I mentioned. They tend to be really complete. You can look at the spec. If you're looking at an isolated test of a subject, it tells you the entire universe as far as that subject cares. Everything it collaborates with, everything that it does is all there in the test. And so I can read that test and fully understand what the subject needs to do. I could destroy the subject and probably rewrite an implementation, probably more easily from an isolation test than from a traditional unit test. And it's also easy to extract, as a result of that, it's easy to extract the code from the application to the library. So if I have a traditional unit test and I'm depending on a whole bunch of other real stuff, and I find that this object is useful generally and I want to pull it out into a gem, I probably have to throw away my tests, because my assertions are assuming the behavior of the stuff that guy depended on, and I don't want to extract those things, I just want to extract this guy. And so when I pull it out and I start a new library with it, I've got a paint by numbers example of all the different collaborators that it has and what it needs from those, what its contract is from those, so I know what other responsibilities I need to fill in. It's been hugely helpful in me extracting code out and building little libraries as I go and then contributing those as open source. Cost is that it requires a tremendous amount of focus, discipline, practice, and because it's weird, courage. A lot of teams, this is a hard sell. And so if you're on a team that doesn't practice this, you either have to sell it or fit in with the team, right? Awkward in-between tests. So not every test is purely isolated or totally end-to-end. What do we do about those other ones we talked about, like regression and characterization and stuff, where some amount of reality is necessary? I don't have a good answer for that. I've been toying around with the idea of having numerous test suites, 3 or 4 or 5, and organizing my test suite by what's my motivation. Having a folder for characterization tests and having a folder for design tests and having a folder for end-to-end tests and running those all as separate, discrete suites. That way I don't really have this problem. I haven't really gotten a chance to try that yet. Also, it conflicts with the Rails way. We're going to talk a little bit more about that. So a question that I've had for a long time, because up until a few years ago I was doing Goose-style isolation test-driven design on Java projects, full disclosure. I've always wondered, why do so many Rails users hate using test doubles? And we've already kind of alluded to some of them. And I think it's just a fundamental attribute of the Rails architecture. And it's not bad, although I didn't pick a particularly flattering picture of a roller coaster. But it's a fact, and it's just something we have to deal with, and we can't really, we have to acknowledge it and work through it. So the train of thought that leads you to the answer architecture is, well, what are test doubles really good at? Answer, they're good at writing isolation tests for our subject code. Subsequent question, well, what does isolation test require that the author do? The answer is that an isolation test has to first identify and then replace all of the code on which the subject code depends. Okay, so well, what does my subject code depend on? How much does it depend on? And the answer is, this is a new term here, inherited surface area plus the surface area of its collaborators. I only recently learned this term surface area, but I love it. The idea is, if you think of your volumetrically about your object, and it has a bunch of methods on it and a bunch of properties, the number of publicly accessible things that I can ask of it, that's its surface area. So if it's got 10 methods and 4 properties that I can get, its surface area is 14. And the smaller surface area, the easier to isolate. The bigger surface area, the harder it is to isolate it from its collaborators. So here's, talking about inherited surface area, I started a brand new Rails 3.2 app. I created a new active record extension called foo, just to see what out of the box, how many methods I had. And I saw that there's 301 public methods just on that object, not counting its collaborators and not counting who it talks to. Now that's not a surprise, right? We all know that the Rails objects come with a lot of convenience. The whole humane interface versus minimal interface argument from back in the day. Isolating that would be really, really hard and probably foolish. I've talked with several people about trying to fake out AR base and figure out what would we have to do to create a smart test double of active record bases, and it's just too much, and it would probably be obsolete as soon as we got it working when the next version came out. And so a more general point, Rails aside, isolation really gets hard in these two situations. One is when you extend classes, your code is extending framework classes that you don't own, because you don't know what it's doing, and you don't know what assumptions that code is making. In the case of AR base, it's all assuming that there's a database there. And so to isolate it, you have to fake out stuff that it's inheriting from its superclass, which there's never a clean way to do. Isolation also is really hard when loading classes is expensive. So in this case, in most Ruby projects, because Rails class loading can take a long time, we find a lot of libraries let you create what Jim Weirich has termed fantasy tests. A fantasy test is a test that uses mocking, and that mocking doesn't do any sort of runtime check that the method that you're using or the way that you're using it in your test double is how the real class does it. But we haven't loaded the real class because it's expensive to load all the real classes, and so then we end up with these tests where if we were to change that method name, all of our tests would stay green, hence fantasy tests. So you can choose that, or you can choose relatively slow isolated tests, because every time you run a test, you need to load up all the classes. So neither of those are ideal. And so as a result of all this reflection on Rails and spending the last year or so thinking hard about this, your options are limited, and none of them are great if you're trying to use mocks for the purpose of isolation testing inside of Rails, the whole goose way. One is you could employ test doubles in your Rails integration test, which we already talked about, this mix and match thing, which I think is a really bad idea. It's a Band-Aid, and it really hams things up for the person who has to come to that code next to try to make sense of how that test is really working and what the story that test is trying to tell is. Another option, you could write a whole bunch of plain old Ruby objects, build a domain-driven design little island here, and then just treat the Rails objects, your active record base and controllers, as collaborators, as dependencies. And there's a lot of merit to that. The problem is that active record and Rails wasn't designed to be used that way. These objects were designed to be extended, and it's really awkward to use them as collaborators. They're not particularly good collaborators. And so I wouldn't say that's a fault of Rails necessarily, it just wasn't designed to be that way. But there's a lot of people going around to screencasts and telling people that this is the right way to do stuff without necessarily giving the full disclosure of, if you go down this way, yes, you'll have your own little tidy domain of objects that you're using. But you're going to end up writing a lot of code that's going to look duplicative to anybody else just for the sake of having these nice isolated tests. It sounds crazy to the average person, I think. You could write true integration tests for your Rails objects, just let them be what they are, not use test doubles when you're testing Rails objects. When you're doing new functionality, build collaborators as you go and try to minimize the number of Rails objects that you need. Or you could just stop extending Rails objects, which means stop using Rails. Those are really your only options if you want to go down the Goose isolation test-driven design path. The ones that I know of, anyway. If you've got a silver bullet, let me know, please. So if you're looking for more on this topic, because we're low on time, I wrote a post last year, just kind of a survey of the different test double libraries for Ruby, from Mocha to FlexMock, what I didn't like about them, and then because I was new to the Ruby community and I wanted to fit in, when I had a slight nit to pick with a library, I decided to throw it out and write my own. So here's a Gimme, which is a little test double library that I wrote that you might like. I don't know. I like it. But I unfortunately don't get the opportunity to use it a whole lot. So if you do use it, there might be a few rough edges. All right. So my company's name, and this is the punchline, my company's name is Test Double, which is appropriate for today. And that's my Twitter handle is Searls on Twitter. I'd love if you follow me and give me any feedback about today. And if you need links or ways to contact me, that's a URL where you can do it. So thank you all very, very much for your attention. I really appreciate it.